For centuries, the far side of the moon was a mystery, a hidden hemisphere of ancient scars and silent secrets. Then, in 2019, a mission changed everything. Ground-penetrating radar revealed something astonishing beneath the surface, a complicated history of buried layers. These aren't just rocks, they're pages of a forgotten story, a violent past of impacts and volcanic eruptions, rewriting what we know about the moon's very formation. What other truths lie waiting? In 2019, China made history by landing the first rover on the far side of the moon. For months, it trundled across the cratered landscape, sending back grainy images of rocks. Then came something different. Sensors picked up data indicating that the underground layers weren't as uniform as expected. That single clue sparked a new round of questions. What exactly lies beneath this hidden hemisphere, and what does it tell us about the moon's violent past? In this video, we'll piece together the evolving story. Why the far side matters. When most people picture the moon, they think of the same pattern of craters and dark patches that hang in the night sky. That side is all we could see for most of human history. But the moon keeps one face turned permanently toward Earth. This locked rotation, called synchronous rotation, means the opposite side is always hidden. For centuries, that far side remained completely unknown, only brought into view when spacecraft first circled the moon in the late 1950s and 1960s. Those first images stunned scientists because the hidden hemisphere looked very little like the side we thought we knew. At first, researchers assumed both sides should share the same main features. After all, the moon formed from a single body and orbits in a balanced way. Yet the photographs and later orbital measurements revealed a striking contrast. The far side has a crust estimated to be much thicker, and it lacks the wide dark plains, called maria, that dominate the near side. Maria are basaltic plains formed by ancient lava flows. They cover about a third of the near side, but on the far side, they are almost absent. Instead, bright regions called highlands stretch across most of the surface. Highlands are older, more reflective, and heavily cratered. This imbalance between the near and far sides quickly raised new questions about how the moon cooled, solidified, and resurfaced after its violent beginnings. One example shows the importance of studying this terrain. Near the bottom of the far side lies the South Pole Aitken Basin. It is about 2,500 kilometers across and nearly 8 kilometers deep, placing it among the largest impact scars in the entire solar system. The basin likely formed more than 4 billion years ago when a massive asteroid struck the moon. Scientists hope that by studying material from this basin, they can reach older layers of the crust or even the mantle underneath, since the impact may have punched through to great depths. No sample from this region has been returned yet, but its sheer size alone shows why direct exploration matters. The consensus view is that the far side holds critical clues for why the crust is uneven. If we can map the underground structure, we can test theories of how magma once flowed, where heat-producing elements concentrated, and why dense lava filled giant basins on only one side. In other words, the far side acts as a counterweight that may explain the missing pieces in current models of lunar formation. The big puzzle is how to actually see below the surface from a rover that only sits a few meters high. Standard cameras or spectrometers only scan surface dust, not deep rock. This is why placing a lander with special sensors on the far side created such a rare chance to investigate hidden geology directly. What those sensors revealed about the underground layers turned out to be even more surprising: the hidden layers below the crust. Instead of finding a simple layer of rock beneath the surface, the Yutu rover's radar scans showed something unusual. The reflections painted a picture of multiple buried sheets stacked one on top of another. These underground layers stretched hundreds of meters deep, and the unexpected patterns made it clear the far side had preserved a complicated record of past activity. The tool behind this discovery is ground-penetrating radar. In plain terms, the rover sends radio pulses into the surface. some waves travel until they hit a boundary where materials change, such as from loose dust to solid rock. At each change, part of the signal bounces back. By measuring the time and strength of these echoes, scientists can build a cross-section of what lies underneath, similar to how ultrasound works in medicine. Instead of seeing beams of light, they see waves reflecting from hidden features below the rover's tracks. What stood out was how inconsistent the results were compared with what researchers had expected. Models suggested the regolith, the loose, dusty soil covering the moon, should gradually become more compact with depth. Instead, signals revealed a series of distinct layers. Some looked coarse and blocky, while others were smoother, almost like fine ash. Certain layers extended for great distances before being interrupted by debris or broken zones. The profile was much more uneven than the smooth progression scientists had in mind. It helps to picture it like peeling an onion and finding not just repeated sheets, but chunks of gravel in one layer, thin powder in another, and odd streaks in between. The sequence suggested a long history of surface covering, destruction, and rebuilding. Each boundary marks either a volcanic episode or a violent event that dumped material across the surface. Rather than one long period of quiet accumulation, the far side soil holds a catalogue of interruptions. The consensus interpretation is that some of these buried sheets represent ancient lava flows. Billions of years ago, impact craters would form and then slowly fill as molten rock flooded in. Later, new impacts shattered that crust and sprayed more debris. Over time, these processes repeated, building a stack of alternating deposits. This layering points to cycles of volcanism and bombardment, both of which were more extended than earlier models predicted. A working hypothesis is that parts of the far side hosted lava events we did not anticipate given the thicker crust. An alternative hypothesis suggests that many layers may be ejecta blankets, created when rocks blasted out of giant impacts fell back over wide areas. Either way, the finding clashes with assumptions about the far side being mostly dormant. Despite its rarity of broad plains, the underground structure holds signs of past lava episodes and large-scale resurfacing. This means the far side crust did not remain frozen early on, but carried a far richer history. By catching the echoes of these hidden sheets, Yutu, two preserved stories wiped clean from the Earth-facing side. And these preserved accounts push us toward deeper questions about how the moon itself first assembled. What the discovery reveals about the moon's past. A soil profile might seem like a narrow finding, but the layers beneath the far side are much more than a list of dust and rock. They point backward to the event that likely created the moon itself. The leading explanation, known as the giant impact hypothesis, is that a Mars-sized body struck the early Earth over 4 billion years ago. The collision produced debris that later coalesced into the moon. This framework explains why lunar samples are chemically similar to Earth rocks while still showing subtle differences. Yet the new evidence from the far side reveals complexities that do not fit neatly into this single model. In plain terms, if the moon came from the same cloud of debris, both sides should share similar crust thickness and signs of volcanism. Instead, radar scans and orbital studies show that the far side has a crust tens of kilometers thicker than the near side. It also lacks the broad maria, the dark volcanic plains that dominate Earth's view of the moon. Deep layering beneath the far side adds to this tension. The discovery complicates the idea that the moon cooled evenly after formation and supports the notion that its interior was never fully symmetrical. One striking example is the evidence for buried lava layers hidden under the far side surface. According to older cooling models, volcanic activity should have died out quickly due to the thick crust blocking magma from escaping. Yet data show signs of repeated lava episodes filling craters before being buried by later impacts. This implies that heat remained available much longer than models predicted. So the question becomes, why did volcanism persist on one side but not on the other? The consensus view is that the distribution of heat-producing elements within the Moon may hold the answer. Elements like thorium and uranium release heat as they decay. Models now suggest these elements concentrated more in the near-side interior, which fueled widespread volcanism. But the far-side findings reveal that heat sources were not absent there either, only less abundant and expressed differently. This uneven distribution would explain why broad maria dominate one hemisphere, while hidden lava layers tell of quieter but longer-lasting volcanic activity on the far side. An alternative hypothesis suggests the asymmetry traces back to the impact that formed the Moon. According to this view, the material hurled outward and recollected into the satellite did not mix uniformly, leaving one hemisphere enriched and the other depleted. Both ideas are actively tested using orbital mapping and rover data. The broader implication is that the underground layers are not just lunar records. They capture processes relevant to the early Earth as well, since the two bodies share the same violent event. This makes the far side a natural archive of how rocky planets and moons evolved in their youth. The discovery reframes the Moon as a keeper of historical evidence rather than a frozen relic without change. With future missions aimed at this hidden hemisphere, the next steps could uncover even more pieces of the story. Conclusion: the buried layers on the Moon's far side show that its past was not static, but dynamic, shaped by lava episodes and impacts that also shed light on Earth's earliest history. Each underground sheet works like a preserved page, recording changes erased elsewhere. Upcoming missions from China, NASA, and international teams aim to probe these records with new landers, rovers, and drills. Following their progress gives us a chance to watch pieces of lunar history reconnect with our own. The question remains, what other hidden clues still lie beneath the Moon's silent crust, waiting to be uncovered?